Okay, people, gonna give a quick look here at question 4. Sorry about the light now. Probably the shadows are not great. Question 4, 2019. Alright. Now I'm gonna do a lot of this freehand, but it'll be grand. So question part A. So select any 2 from 3 right and explain the difference between, okay, a cooling curve for an alloy, a cooling curve for a pure metal. So an alloy cooling curve. So the cooling curve and a pure metal. Okay, so what you've got here is time on the horizontal axis, and here you've got temperature. Okay, so I'm going to do the pure metal first because I prefer that. So let's say you heat a metal up to a random temperature. Let's say this is 500 degrees. And it starts to cool down. I might use a different color for this. Will I, won't I? Decisions. No. Yes. So you heat a metal up to 500 degrees and you switch off the furnace, and it's a pure metal, so it starts to cool down. So after as time goes along here, it's cooling down. So let's say after, like, you know, maybe 15 or 20 minutes or something, it reaches its melting point and it stops cooling down, and it stays like that for maybe a half an hour or something until it's completely solid, and then it starts to cool down again down to 0 degrees. So here it's melted, here it starts to solidify, here it's fully solid. So that's where you've got like dendritic growth and grain growth and crystals and all that stuff going on there. So it starts there, finishes here, no change in temperature. So that there is the melting point, which is also the solidification point. Okay, so for a pure metal, it's like that. Now, if I take an alloy then, so let's say you heat an alloy up to 500 degrees and it starts cooling, like that. And when it reaches a certain temperature, it begins to solidify, maybe fully solid, and then parallel again to that down to 0. Okay, so for an alloy, okay, so here it's liquid or molten metal, starts to solidify, and by here it's fully solid. Okay, so you can see here an alloy does that as it's cooling. So it cools and solidifies at the same time, whereas a pure metal stops cooling as it solidifies. Now the reason for that, it's to do with the what's called the latent, which is hidden, heat of fusion. Okay, so what keeps the temperature the same there is the energy of the atoms connecting and bonding onto each other. They give off energy and heat when they're all linking up and forming a solid structure, and that maintains the heat at the same temperature until it's fully solid, and then it cools down the rest of the ways. And would you want to be writing that down in the thing? I suppose you would. So for the just checking that's on camera there. So for the solid begins to solidify and finishes the process at the same temperature. Whereas an alloy for an alloy the temperature drops during solidification. So you can see there lower temperature there as it's happening. And the reason for that is because if we just look at the equilibrium diagram for an alloy, you'd have two metals with different temperatures, maybe, you know, metal A and metal B. So one of the metals has a lower temperature than the other. So one of them starts to solidify at a certain temperature, and the other one is fully solid at a lower temperature. So that's why this works across a range of temperatures, whereas a pure metal, there's only one metal there rather than metal 100% A and 100% B. So that's why they behave differently. Now the second one there, okay, is amorphous and crystalline. So versus crystalline. So an amorphous material, I'll just write it here, has a structure, and crystalline has no structure. So I'm just going to draw a structure, and I'm going to draw some atoms with no structure over here, and I might even put some interstitial atoms in between here. Beautiful. Okay, so you want a simple, God, I think that might have been off camera. So what you want to do there is just put a pattern, a regular straight line pattern of atoms with different, you know, smaller atoms there. So it's an alloy. This, I'm just using an alloy as the example. So like that has a structure, this has no structure. In terms of plastics, even though this is a metals question, but it's the same idea with polymers or plastics there. When you're showing the amorphous in plastics, you're just showing a definite pattern, whereas a crystalline polymer is like spaghetti, they're just everywhere. So that they're a pleasure to draw. There's no structure for them. So that's amorphous versus crystalline. And the last one there, the eutectic point versus the eutectoid point, you need to really be doing the iron carbon equilibrium diagram for that. So I'm going to leave that out because it's a question we don't do. All I'm going to say about that is eutectic is where an alloy behaves and like a pure metal, going from solid to liquid at one temperature. And a eutectoid, it's where an alloy changes its structure at a single temperature. So like steel goes from FCC to, no, this is not what you want to be doing in an exam, FCC to BCC at one temperature. That's 4.3% carbon at 1140 degrees, I think. But as I say, it's a question that we don't cover, so I won't harp on it a while on here. So, just make sure now that we're in shot for this anyway. Now, the diagram. So what we want anyway here is we want 100. We want 100 mils or 10 equal distances here across that. I'm just going to go with 100. Okay, so that's 0%, and this is 100% of A. So just going to stick some temperatures on here now. And I'm going to put on all these vertical lines here now as well in one go. Just in pencil now, a small bit lighter with pencil. Now I'm going to draw them a little bit heavier than I normally would because I want them to be visible, but now in an exam you'd be using graph paper possibly, but it doesn't really make that big of a deal. Okay, so what we've got here is I'm checking the temperatures here now, and the lowest temperature 140, highest is 310, 140. Okay, so I'm going to put the 140 down here because we don't need it going down to 0. 140 is the lowest temperature and nothing happens below that, nothing. So we don't want a whole lot of space wasted for nothing. So there's our my 140. So 160, 80, 200, 220. I'll label all these 220, 240, 260, 280. 300 degrees C and 320. So that should cover all my temperatures, 160, 180. Okay, So so at 0 degrees starts to solidify at 268. So 268, 270 would be there. So there's my first point. So not 10, 20, 30, 40. Okay, so 10% cadmium. Okay, so this is my percentage of cadmium. So 10, it's 237. So 220, 237 would be there. 20 is 205. 205 would be a quarter of the ways up. 175. Then 140. So basically that here, it's not exactly a straight line, but it's fairly close to it. And then going the other way then, at 50% cadmium, it's 190. 60% cadmium, 235. 70% is 265. 80% is 290. 90% is 310. And finally 321. So okay, so that's our diagram drawn. Now we want to label that. Now ideally I would have left a bit more space for labeling this here, but I'm going to label this now. So this is liquid. Everything below here is solid. Now I'm going to just label this yellow line here. Just going to say that that is what's called the upper critical temperature. And I'll just use red here, it'll do for the lower critical temperature. So that's, and this is pasty what? Pasty. Can never remember. It looks better with an E. So I'll have to check that spelling now or I won't be happy. Okay, so it's P-A-S-T-Y. I think I'd know it at this stage. P-A-S-T-Y. Okay, so that's pasty is a mixture of solid and liquid. Alright, so that's it drawn, labelled, and just highlight as well that down here is all solid and up here is all liquid. Alrighty then, so just check this here again now. So draw the equilibrium diagram, label it and describe the key features of this diagram. Okay, the key features. Okay, so this is eutectic alloy. Okay, now where the two metals don't really want to mix, so they form layers. Okay, so now the other kind, right, of equilibrium diagram is the solid solution one. Okay, so I'll just put that in brackets that it's different to a solid solution, which always looks like this. They're the ones that look like this, where the two metals are happy to mix. Okay, so that's a eutectic alloy where all the atoms mix happy out when they're in liquid state, but when they solidify, they separate into layers. And the last thing there is this here is the eutectic point. So that's the eutectic point there, and I'm just going to say there that the eutectic point is the mixture where the alloy behaves like a metal, like a pure metal. Why do I say that? For every other mixture, it starts to solidify and you got to heat it hotter to get it fully liquid. So for every other one melts across a range of temperatures, but a 40% cadmium mixture melts and solidifies at 140 degrees. Okay, so it behaves like a pure metal, so which is a single temperature. Okay, so pure metals have an exact melting temperature, and an alloy has an exact melting temperature at the eutectic point. So what else were we asked to do? So label, describe the key features, and explain eutectic alloy. So that is what a eutectic alloy is. It's a metal that doesn't want to mix, and that there's one special mix that behaves like a pure metal. So I'm going to just say that this is what a eutectic alloy is. Okay, so again, that's not fantastic there now. So 1 is drawing it, 2 is label it and describe the key features, and 3 then down here is to explain a eutectic alloy. So that would be done. Now see there then, it shows a photograph of dendritic growth as a metal solidifies. So describe the stages of dendritic growth. Now again, I'm going to do exactly what you shouldn't do here now, and that's I'm going to squish it in down here at the corner so that like I'll have it on two sides of a page. So dendritic growth, normally say just pick 3 or 4 circles there. So These are called nucleation points. So that's where now that's where you've got a liquid and a couple of points there where inside in a liquid metal. So I'll just label this is liquid, and just at some random locations it begins to solidify. Now if it was steel, you might even add talcum powder to cause these to start, or it could be around bits of dust or dirt or something like that. But anyway, when you cool down a metal, it begins to solidify. So that's nucleation points. Now these get slightly bigger, and this is called grain growth, and bigger as more and more solid. So there's less liquid, so less liquid. So as we can see there, that's the liquid, and eventually you end up with so we're going to end up with 4 grains. So there's 4 crystals or grains, and then it's fully solid, no liquid. Okay, and the word dendrite is Greek for branches or needles. So it's kind of like frost on a windscreen, that kind of spiky thing there. So like it was shown in the photograph anyway, but it's basically that idea of spiky needles of solid growing into liquid. So that is describe the stages. And the last thing there then is name 2 defects that may occur during solidification. Okay, do not do this in an exam, but I'm going to stick them in here. So point defects, I'm going to draw just a couple of atoms. And okay, so there's some atoms. So 2 defects. So number 1. Okay, so defect number 1 is a vacancy. Not sure if that red comes out here now, but this is here. I'll just put in here defect number 1 is a vacancy, which is a missing atom. And 2 is an interstitial. Which is a small atom in between the other ones. I'll put it in here in green, and I'll call that there number 2. So number 2 is an interstitial atom, which is a small atom. Now you'd want to be describing that as well, is a small atom in between the bigger ones. And another one I could have put in if I wanted is I could have put in a substitution, which would be a different kind of atom altogether. That would be a substitution. which is a different kind of atom completely. That's a third one, which is a substitution. So again, do not do that in an exam now, of lumping them all in on top. You'd go on to a new page there and start and just put it there and write a few lines explaining every one of them. So yep, that's question 4.